Now, a force vector. Well, a force vector is going to measure the force imparted on an object and the direction in which that force is imparted, okay? So the force vector measures, let's say, the amount of force on an object and the direction of that force. Or I'll say the direction in which that force is imparted upon that object. I'll just say is imparted. So a force vector measures the amount of force. Now, this would be the magnitude. The amount of force, if F represents your force vector, then the amount of force, the length of that vector, is not measured in distance. It would be measured in pounds or something called newtons. So the length of that vector is the amount of force imparted on that object, and the direction, the vector gives the direction also, and that's just the usual theta. In this example, a 120-pound force keeps an 800-pound object from sliding down an inclined ramp. Find the angle of the ramp. So these problems are intimidating at first until you realize you draw them all the exact same way. So stick with me while I draw this out, and then I'll show you that they all kind of work the same way. So you're going to draw the horizontal. What would be the horizontal? And then the ramp against the horizontal. So and I really don't pay attention to what the incline might be. I just draw an incline. I don't care if it's accurate. And then we've got an object on the ramp. Let's say it has wheels on it, so it's like a motorcycle or cars, maybe 800 pounds, so maybe a motorcycle, big motorcycle. And so there's not a whole lot of friction going on. If it moves down the ramp, it's going to go. So this is, that's my okay, wait, it's got to have a gas tank. There it is. There's my motorcycle. That's not the important part of the problem, drawing that. Yeah, it does look more like a bicycle, you're right. So we're actually looking for the angle of the ramp, which is this guy. Okay, you're going to have a vector pointing straight down due to weight, right? Gravity, your weight, we think of it as pointing straight down to the center of the Earth. Or just, since the Earth is such a big sphere, we kind of think of the Earth as being flat, even though obviously it's not. And the weight vector pointing straight down, okay? So let's make the weight vector, we'll put that in blue, and we'll make that point straight down just from the center of the object, straight down. You can make it as long as you want, doesn't matter. So that's gonna be the weight vector. And we know the weight is 800 pounds, so that's gonna be the magnitude of it. So if you call this thing W, this guy in blue W, then it's really the magnitude of W. That's 800 pounds. Does that make sense? Because that's, when we're talking force, the magnitude is the force imparted, in this case, against the ramp straight down. Okay, the length of it is the magnitude, is the 800 pounds. Now, it can be shown that you can break up any vector into two components that are added together. So triangle law, we should be able to find two components we can add together, and two component vectors, and add together and get W. And the ones we're interested in the vector that is the force vector perpendicular to the ramp, okay? So we'll do that one in green. The force vector perpendicular, so it makes a right angle. This vector in green should look like it's making a right angle with the ramp. Close enough. And that's going to be a certain amount of force. We'll call that's the force. F1 is the force against the ramp. F1 equals force perpendicular to the ramp. So I'll use that symbol upside down, T it looks like for perpendicular to ramp. And what you can show is that there's a vector F1 you can add to F1 that's a force vector parallel to the ramp, and you can add those two together and get W. So what do I mean by the force vector parallel to the ramp? Well, there's a couple different ways to think of it, but you could think of it as the force exerted by the motorcycle in line with the ramp, parallel to the ramp. But we can put that vector down here. We'll call that vector, so we're putting a copy of that orange vector down here, the force parallel to the ramp. We'll call that F2. And that's the force parallel to the ramp. Okay? And it can be shown experimentally, if nothing else, that W, the weight vector pointing straight down, is equal to F1, that's the perpendicular force against the ramp, exerted by the object on the ramp, plus F2, that's the force exerted by the object parallel to the ramp. That's the force you have to overcome to keep the object from moving down the ramp, right? From sliding down the ramp or rolling down the ramp. So this is the result we're going to use here. So that when you draw this picture, it's going to look the same every time, except for maybe the length of the vectors. That can vary depending on how, I don't care how long you draw these things, how long you make them. But when you draw it, this should look like a right angle right here. Because F1 is perpendicular to the ramp, F2 is parallel to the ramp, so they must be perpendicular vectors, right? And then you should be drawing W, the weight vector, so that it points straight down. Okay, so that's the only complicated part of this problem. The rest of it is going to end up being SOHCAHTOA because we're going to treat this triangle that we've created with the blue, green, and orange vectors, we're going to treat it as a regular old triangle because all we're looking for here is an angle. In other cases, you'll be looking for a magnitude, which is the length, a length in the side of the triangle. So what we'll do then is we'll separate this out, this triangle that we've created. And you don't even need to draw the arrows now. So this vector in blue has length 800. The 120-pound force that keeps the object from moving down the ramp, that's got to be the length of F2. It's got to be the magnitude of the force parallel with the ramp. So that would be the length in orange right there. That's a right angle right there. And then my claim is this angle right here also has to be theta. You guys see why? It's because this angle that W, the vector in blue, makes with the horizontal, since it points straight down, has to be perpendicular. Perpendicular to the horizontal, which means this angle up here has to be the complement of theta. And then this gets a little complicated, but this angle here has to be a right angle formed between the ramp and the vector in green. So this angle here then is the complement of theta, which is theta. So looking at that triangle, we have enough information in it to find theta. Okay? So look at this triangle. That's the same as this triangle. Theta right here is the same as this theta. We've got enough information to find theta, the angle of the ramp. Yeah, in fact, what trig function thinks SOHCAHTOA relates theta and the opposite side and the hypotenuse? Okay, so sine of theta equals what? 120 over 800. Let's take the sine inverse of both sides. Run that through your calculator. Just give me an approximation to one decimal place in degrees. What do you get? 8.6? Is that? I have confirmation, Mission Control. Okay, 8.6 degrees. Now, here's the good news. Anytime you get a problem like this, okay, you might be given theta in other problems, and you might be looking for F1, the force perpendicular to the ramp, or F2, the force parallel to the ramp. But it all goes back to drawing that triangle and using SOHCAHTOA, okay? So these problems, if you can draw that triangle, now I'm going to force you to draw this picture, of course. And then if you can separate it out and draw that triangle, you can find the missing bit. So all your pictures are going to look like this. It's just you might know theta and not know this number, or not know this number, okay? And then you just use whatever trig function you need to, use SOHCAHTOA to find the missing bit. So it goes back to right triangle trig after you draw it.